So we just talked about Riemann-Stieltjes integral, where this capital F was this function with a jump discontinuity that placed all of the weight of the integral at a single point. So at the kind of opposite extreme is, what if f prime has a continuous derivative? So let's say capital F prime is this function phi, and that phi is continuous. Right? So let's look at what happens in this case. For any partition of our interval AB, by the mean value theorem, for each interval in the partition, I can find a sample point in between xi minus 1 and xi, such that this difference, f of xi minus f of xi minus 1, equals the derivative at the sample point times the length of the interval. Okay? This is by mean value theorem. Okay? So this Riemann-Stieltjes integral in this case becomes this capital F of xi minus capital F of xi minus 1 is equal to phi prime of s times xi minus 1. So just put this, replace the left side here with the right side here, and I'm doing the sum at the sample points si, which came from the mean value theorem. And so I have this, which is a Riemann sum in the regular sense, just for the function f times phi, not phi prime. F times phi. So this is an actual Riemann sum in the usual sense for the function phi. And so as I take this partitions to be smaller and smaller, these are going to converge to the integral of f times phi. So let's think about this in terms of the weighting function. So we said that these Riemann-Stieltjes integrals allow us to weight the integral, so we can have higher weights at different points. Right? So here, since f is non-decreasing, right? So we had this capital F function, and it was non-decreasing. It was also right continuous, but that didn't really matter. On this page, we're assuming it's differentiable. Right? So here this is non-decreasing. So if it's non-decreasing, the derivative is non-negative. And so this phi function here can be thought of as a weight function. So where this phi is large, I'm applying a larger weight to that portion. So if I had, for example, a function like this, right? So if this is my function phi, I'm going to apply very little weight, zero weight, near zero, and higher weight away from zero. Okay? So this phi can be thought of as placing a different importance or different emphasis at different x values. So here I would place low emphasis on the parts with low weight and higher emphasis on the parts with high weight. Okay? So if you know about CDFs and random variables, you can understand this in terms of a capital F is a CDF and this is a PDF. Okay? Also going to talk about Lebesgue measure. I only have one page on Lebesgue measure. Just want to introduce the definition of it and mention some facts about it. Okay? So if you want to really understand Lebesgue measure and see the important aspects of it, you're going to want to take a measure theory course. Okay? So Miami offers a measure theory course. So for any subset A of the real line, we define lambda star of A to be the infimum of sums like this, where taken over the sets of all intervals which cover A. So I want to take a bunch of open intervals that cover A, and I want to add up all countably many of their lengths, and take the inf over all the different sets of intervals that I can use to cover A. Okay? So this lambda star of A is defined for every subset of the real line, and it's a generalization of the notion of length. Okay? It's called the Lebesgue outer measure of A. Right? If you restrict lambda star to certain subsets of the real line, it's called the Lebesgue measure, but we're not going to get into that. If you want to know slightly more about that, you can send me an email, ask me a question. If you want to know a lot more about that, then you take a measure theory course. But this is the Lebesgue outer measure. It's defined for any set A. And just a few facts, right? So these are some facts I'm not going to prove. They're beyond the scope. Well, they're not beyond the scope. I'm not going to prove them in this lecture because they're kind of standard facts, things that are like you look at on your own. Lambda star of an interval is just the length of the interval. Okay, so here I'm going to say, right, for this case, right, so lambda star of some non-empty interval is just the length of the interval. Okay? If I have a countable set, then the Lebesgue outer measure is 0. So if I have a countable set, then as far as the Lebesgue outer measure is concerned, it's nothing. Right? It has no length. Okay? And it turns out that there are uncountable sets that still have a Lebesgue measure 0, and you can try to cook up an uncountable set which has Lebesgue outer measure 0. And so if somebody were to ask you to come up with one, you'd have to come up with a set, prove that it has a Lebesgue outer measure 0, and prove that it's uncountable. Okay? So this is 3 kind of important, interesting facts. So I'd recommend kind of trying to figure those out. If you can't figure them out, send me an email, talk about it. So if I have a bounded function on AB, it's Riemann integrable if and only if the set of discontinuities of the function has Lebesgue outer measure 0. So if I take a function, a bounded function, okay, I can look at the set of discontinuities. And then I can look at the Lebesgue outer measure of the set of discontinuities. And this function will be Riemann integrable if and only if that's equal to 0. So I'm not gonna prove this because the proof is very long and tedious, and I don't think it gives any insight. It's a very nice result, but well, in this course we care about the Riemann integral. I don't care about Lebesgue outer measure, and I'm not going to care about Lebesgue outer measure unless I'm talking about the Lebesgue integral, which is kind of the right way to do integration. But so I'm not going to prove anything about this. If you want to see more about this, you can refer to the book. I don't want to say a lot about Lebesgue outer measure if I don't have to, and if we're not in a measure theory course. Okay? So basically everything I want to know about Lebesgue outer measure is contained in these 3 items.